I will start. I will give a lecture on generative AI for image generation. Especially, I'm going to talk about the GAN. It represents generative adversarial network. There are numerous different types of generative AI when we are generating images. And today I'm going to focus on generative adversarial network. You remember that in the previous class, we was talking about transformer model. It has encoder and decoder architecture. And especially in encoder, we have self-attention. And also we have positional encoding method. Input was in parallel and output was generated sequentially. And the connection between output of encoder with decoder was described by cross attention. So as I discussed so many times, the very important feature of transformer model is encoder-decoder architecture. Second, it has self-attention mechanism at the encoder, plus positional encoding. The connection between encoder and decoder was made by using cross-attention matrix, and input is in parallel. Of course, input could be text, image, or sound. Output could be text and image and sound. Another type of generative AI for image generation is called variational autoencoder. Probably next Monday and Wednesday, I'm gonna talk deeply about variational autoencoder method. I'm gonna give you the architecture and loss function and backpropagation. And for the specifically, in the case of variational autoencoder, we have input vector and it has encoder. And output of encoder is latent vector G. In the transformer model, the connection between encoder and decoder waves was made using cross-attention matrices. But in the variational autoencoder method, input data is converted to latent space vector G using encoder. Of course, here encoder and decoder at the transformer model was made of deep neural network. And of course, specifically, in addition to deep neural network, it has self-attention mechanism. Here again, deep neural network is made using deep neural network. That means you have a lot of parameters. And during the backpropagation, this parameter will be determined. Once we have a latent vector, we degenerate data X dash using the decoder. It is made of DNN. Of course, encoder has model parameters and decoder has model parameters. By comparing, so we can define loss function such as x minus x dash square or KL divergence of x and x dash. KL divergence means entropy of input data and entropy of output data. That difference is KL divergence. Sometimes we are using entropy function of output x dash. At this moment, I would like to give you the overall architecture and loss function of numerous different types of generative AI model for image generations. By defining the loss functions, if there is some loss, we can go back to the backpropagation. During the backpropagation, we may need some loss function. In actual case of variational autoencoder, we are defining the loss function by combining these three different types of loss. Sometimes entropy, or sometimes KL divergence, or sometimes mean-square errors. By combining some of them, we can define loss functions. By doing the gradient descent method, we can update decoder parameters and encoder parameters. Of course, we may need many different testing set or training set of X. So probably we may need millions or millions of training set to train model parameter of encoder and model parameter of decoder. Third type of generative AI is GAN. Generative Adversary Network. That is the main subject of class today. It has two parts, quite different architecture. It has generator network. It has latent vector, and it is becoming the input of a generator network. Of course, generator network is deep neural network. In addition to that, it has discriminator network. This is generator. This is discriminator. In the transformer model, we have encoder and decoder. Encoder and decoder are connected using the cross attention. In the variational autoencoder architecture, encoder and decoder are connected through a latent space vector. However, in GAN architecture, it has two distinctively different networks. One of them is generator, the other one is discriminator. When this generator is generating images, it is applied to discriminator as a form of fake X. Of course, you have real X. Let's assume that real X is image of Picasso drawings. Let's assume that this generator is trying to make an image that is very similar to Picasso drawing images. And then output of this discriminator will be Y, that is between 0 to 1. if this drawing, generated image, is very close to Picasso drawing, the output will be 1. If discriminator believe that this is fake image, output will be 0. So generator want to make a good images, and discriminator want to determine whether this is a fake or real images. They are fighting each other until they have 50% and 50% winning rate. So today, later on, we will go more deeply into the discriminator network. The last model is diffusion model. I know that you may be familiar with DALL-E, that is the OpenAI image generation source. They are using diffusion model. Let's assume you have real image. They are adding noise, Gaussian noise, and until it reaches fully noise level. They are having deep neural network to add Gaussian noises, and they are generating, and then at one point they are going backward direction. So by comparing initial image and the reproduced image, we can define the loss function. Probably 2 weeks later, I'm going to spend a week to discuss about the diffusion model. Very difficult to explain. But somehow they are adding noise, and from the noise they are bringing back to the original images. So this is 4 different representative generative AI model for image generations. Let's talk about variational autoencoder. After the training, we have very good model parameter of encoder and decoder. Then after the training, we can use this generator part for image generation. For example, let's assume that you have latent vector who is my face. Let's assume we have another latent vector that is glasses. If we adding those latent vectors together, we can generate new images with my face with glass. So a lot of manipulation can be done in latent space to generate the new images, and this decoder actually transmit or translate latent vector to the real images. In the generative adversarial network, once this generator and discriminator was well trained, then we are using this generator and latent vector space. By having different set of latent vector, and using this latent generator, we can generate new images. Of course, in this diffusion model, after the training, we can use this back direction, that is denoising process. From the noise, we can generate images. By having many different manipulations and mathematical calculations, we can generate new noises. By having this deep neural network of denoising process, we can generate new images. The common thing here is that probably we are using latent space and noise spaces. Probably these pictures are space of human being. We understand what is this. But here, it is almost impossible to describe. But probably this is God's language. we cannot understand. But somehow we can transfer images to noise level, and we are able to bring it back to the human images by the help of deep neural network of AI supercomputer. And somehow, in the human language level, it is very difficult to describe on images. Probably to explain a picture, we may need a whole book of explanation. But in the noise level, probably a set of noise vectors that describe our reality. That's my philosophical understanding of generative AI for image generations. So probably for the next 4 weeks, I'm gonna talk one by one each other. At the end of after we discuss this diffusion model, I'm gonna talk about the reinforcement learning. And sometimes when we are designing new architectures or hyperparameters, we may need to optimize what is the right answer or what is the wrong answer. Probably the reinforcement learning will help us to optimize our architecture and model parameters. That's why in December, I'm going to spend a couple of weeks to talk about the reinforcement learning. Now let's focus on generative adversarial network. It was first introduced in 2014 by a scientist called Ian Goodfellow. I think this diffusion model was mostly very becoming popular in 2023. I think every 5 or 10 years, we will see new models that are surprisingly efficient and accurate. Now let's assume we have noise, G vector space. It will by using generator, let's assume we have latent vector G, and generator will convert this latent vector to a certain image. Let's assume that it is the image of number 8. From latent vector to image conversion will be done by convolutional neural network, CNN type network. At the end of the class, I'm going to go a little bit deeper into this. Smaller dimensional vector can be converted to 8 by 8 or 16 by 16, or it can, by adding some mathematical manipulation, we can expand the size of vector to an image scale. That mathematical manipulation is called convolution. It is not a difficult mathematics. Later on, at the end of class, I'm going to talk about that. Then we have training set. Training set is gonna have X real. This image generated by or generated from a latent vector is called X fake. X real is real image. X fake is generated image from using the latent vector G and convolutional neural network. Convolutional neural network is kind of magnifier of matrix size. Small vector space to larger vector space. here also we have clear image of number 8. It will go to the discriminator. It will convert to large image to small image by having convolution process, and finally it's gonna have number. So from latent vector G, we generate fake image, and we also have real images. By comparing that, that means deep neural network is doing that capability, functionalities, and mathematical process is convolutional process. Later on, at the end of the class, I'm going to explain that. At the end, you're gonna have a number. If the fake image generated by generated neural network is real, output is gonna be 1. And if this is completely fake image, output is gonna 0. So generator wanna fake discriminator as if it is a real. But discriminator wanna compare real image and fake. And they wanna make a good decision whether this is a real image or fake image. They are fighting each other. This fighting process is backpropagation process and training process. Now, I would like to talk about loss function. I would like to explain this little bit complicated loss function. In the discriminator, we have model parameter D, and generator, we have model parameter of G. Now, what is the very interesting loss function is like that? Let's talk about this means we have to train discriminator parameter theta D to maximize this loss function. How can we do that? Dx should be equal to 1. This is actually x real. This is actually x fake. What this means is that, this is a log function. To maximize this, dx should be equal to 1. And this part should be equal to 0. So you have to train discriminator so that real image discrimination is equal to 1 and fake image discrimination should be equal to 0. This is a way to train discriminator. Discriminator has to know what is real, what is fake. Discriminator has to train so that fake image output should be 0 and real image output should be 1. That is the mathematical description of maximizing loss function by training the discriminator. So to train this network, first you have to train discriminator so that discriminator should have such an output so that if your input is real, the output should be equal to 1, then log 1 should be log 1 is equal to 0. And your discriminator input is generator output that's fake, that should be 0. Then this term also becomes maximum. And that means you have to apply gradient ascent so that this loss function should be maximum by having discriminator network parameters. I'm sure that is a little bit confusing to you, but just write it down and remember. Sometime later, if you are going to use the generative adversarial network, you will be much more confident and you will have much easier time to understand. So once again, today, from now on for a couple of weeks, I would like to introduce you a few generative AI model. And today, specifically, I'm going to talk about GAN. Very interesting architecture of GAN is they have two different deep neural networks. One is for generating the images from latent space. Second one is discriminator, which will determine whether it is a fake or real images. And they are trying to train discriminator network and generator network. Once it is well trained, by manipulating the G space, we can generate new images. That is the main idea. Then, when we are training the discriminator, what is the loss function? Here I'm showing that. What is the meaning of that? Discriminator should have certain capability that if the input is real, output should be 1. Input is fake, output should be 0. Then this log function will have maximum number. You remember that log function has this kind of curve. So maximum point is when d is equal to 1. This is the first term in this expression. I'm very sorry that I give you big pressure to you, but explanation of diffusion model and variation autoencoder is 10 times more difficult. It involves more mathematics. Now, how are we going to train the generator? We want to train generator so that this loss function is minimal. How can we achieve that when G is equal to 1. First one is not controllable by generator network. Only second term. This is becoming minimum when this number is near to 0. So that means this is becoming 0. That means this term is equal to 1. What that means is this is fake image. Generator want to make a fake image so that discriminator doesn't know whether it is fake or real. This output is equal to 1 is we have to train generator so that discriminator seems to make a decision that, oh, this is real. So this is a kind of fake action of generator. So generator want to make a fake action. Discriminator want to know whether it is fake or real. They are fighting each other. This is the main principle of learning process of generative adversarial network. Let's talk a little bit more about the meaning of this loss function. Let's assume that we have a function that has a log y minus plus b log 1 minus y. Very similar shape. Differentiation of j is becoming what would be the best y to have optimal point, and I'm doing the differentiation, then equal 0, a 1 minus y minus b y is equal to 0, then y is equal to a plus b. This is not a very rigorous representation of loss function, but to give an idea of what's going on, this is y is discriminator output. Discriminator output. What is the D who has maximum condition when y is equal to 1 of 2? That means this is becoming 1 over 2. This is becoming 1 over 2. That means discriminator winning percent is 50%, and generator winning percent is 50%, and discriminator winning percent is 50%. They are competing each other, and the winning rate is just becoming 50%. Generator is generating images so that discriminator does not know whether it is fake or real. Discriminator cannot find whether it is real or fake. So this is a condition where real and fake images cannot be distinguished each other. I think this is really a condition. X fake is almost X real. So two conditions maximize this loss function by training the discriminator. The second condition is minimize this loss function so that we train the generator network so that this term is becoming 1. Now, let's assume that you have latent vector G who has man with glass. And then we may have another one G2 that has man without glass. And we add another latent vector G3 that is woman without glass. Then it is going to generate images. Woman with glass. So let's assume that after the training, we have very good discriminator and we have good generator. Then we are going to use the generator and latent vector G. Let's assume we have latent vector G1. It has an image of man with glass, and then we subtract the latent vector who generated man without glass, and then we add latent vector G3, woman without glass. So with glass, without glass, without glass. I'm a little bit confusing. Man minus man plus woman means woman. With glass, without glass, without glass. Minus plus, it canceled out and glass will remain. So we're going to have new images, woman with glass. So what I would like to say at this moment is that once we have good generator and latent space, by having manipulation in latent space, we can generate new images. Sometimes, who is going to generate the G? We can start from the random noisy vector, or sometimes this G vector can be converted from the text image, text. So then we may need a conversion from text to G matrix. Usually that is made of encoder. Now, let's move on to this generator network. First, I would like to give you an idea about what is convolution. When we are expanding from G space to real images, we have to make a larger and larger data space. during that process, we are doing the convolution process. Convolution, if we have a 2 by 2 matrix and 2 by 2 matrix, convolution is becoming a single element, multiplication of each element in sequentially. And actually, when I was saying that when we are training this generator, we have to optimize generator model parameters such that loss function of this should be minimized. Minimized means the discriminator output of generator input should be equal to 1. And during that process, we are applying this convolution. So this filter is actually generator model parameter. So during the back propagation to minimize this generator network, we have to determine F1, F2, and F23, and F4 using the gradient descent method. When they are expanding small size vector, let's assume that it has 16 by 16. Next step, it becomes 32 by 32. Next step is becoming 128 by 128. The vector size is becoming, matrix size is becoming larger and larger so that until it has a real images. And activation function is actually used to ReLU function. ReLU function is kind of rectified linear function. And at the final stage, I know that they are using tangent hyperbolic activation function. So depending on different papers or different models, they may have different. But usually when they are using convolution, activation function is usually using the ReLU function. At the final stage, they are using tangent hyperbolic function. Then how are they expanding the images during the generating process? Let's assume that we have initial image like that. It has 1, 2, 3, 4 elements. It is adding some zeros. They are adding zeros. So it is becoming 2 by 2 matrix is becoming 4 by 4 by adding some numbers. Probably depending on model, they may have different initial numbers. They are adding some numbers. That is how they are expanding the small size images from latent vector to real images. Then they are applying this convolution. 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 One step by one step, they are applying filter, and they got new matrices. This is a kind of filtering window. They are applying the convolution. They got new number. They are applying the convolution. They got new number. They are applying the convolution. They got new number. Basic process is convolutional filter multiplication. Then they are adding some dummy values to expand the small images to large images. Of course, these filling numbers might be another parameters we have to train during the backpropagation. This process is called as fractional strided convolution. Fractional means you are adding some zeros. And stride means you are applying the convolution, then you move next step, certain step. In this case, stride is number 1. We are moving one step, and got new number, we are moving one step. That is this stride wording is coming from, originated from. Then we are applying convolution. Once again, I would like to remind you that during this fractional strided convolution to expand from G space to real images could be 256 or 256 images. We are doing this. So during this expanding process, we have to apply the convolutional filter. And this one is model parameters we have to determine during the training processes. Of course, after this convolution, we have to apply ReLU activation function. If the output is larger than ReLU function is a kind of rectifying function. Output is smaller than 0, it becomes 0. If the output is more than 0, then output is proportional. And at the end, we apply the tangent hyperbolic activation function, means output will be between -1 to 1. Sometimes we are using the sigmoid function as well. And discriminator also has similar process. It starts from 256 to finally it has output y between 1 to 0. Now let's assume we have big images. We are applying the convolution, applying the filter, and then we shift. Stride is 2. Then we apply the convolution and convolution. By controlling as a stride, if we have jump around, we can reduce the matrix size to smaller one, as 2 or 3 or 4. Stride means the position of convolution at this. Let's assume that we have 2 by 2 convolution, then we get this number. But we jumped stride 2, we jumped 2 steps, and we got another convolution and another convolution. By doing that, we can convert larger size matrix to smaller size. Of course, this filter, we have filter, and the filter parameter is called theta d. And also here we are using ReLU activation function, and output is sigmoid, so that it is between 0 to 1. So I would like to summarize my class today now. From now on, I would like to give some lectures on generative AI models for image generation. I want to start from generative advisory network. It was introduced to academic society 2016, just 8 years ago. Now it is no longer useful. There are now people are more talking about diffusion model. Model was introduced last year. But it is good to know the history of generative AI model. Now, most important feature of this generative advisory network is that it has generator network and discriminator network. You remember that transformer model or other models has encoder and decoder. And they are manipulating in the G space to generate new images. So during the backpropagation, they are training encoder and decoder as well. And loss function is KL divergence, entropy, or mean square error, whatever. But somewhat distinctive difference between the another model is that here we have generator network and discriminator network. And generator network expand from G space to real images. And mathematical process is a kind of convolution. And they are applying the convolution, they have to certain filters. That filter parameter is actually the generated model parameters to be trained during the backpropagation. And also discriminator has a deep neural network which starts from images, and output is gonna be whether it is real or fake. And of course, during the training process, we are using the deep neural network and especially the convolutional neural network style. And in order to apply the convolutional neural network, we have to have a filter. And that filter parameter is actually the parameters to be trained during the backpropagation. Now, how are we gonna train the discriminator and generator? And this is a min-max loss function such that output of real should be maximized. That means output discriminator output of real images, discriminator output of real images should be equal to 1. And output of fake image, if input is a fake image, output should be 0. Then this whole term is becoming maximum. That means this first training of discriminator is we have to train discriminator so that it is becoming smarter and smarter, so that it knows what is real images and what is fake image. Fake image is generated from the generator. Second objective of this loss function is we have to train generator so that discriminator feel like, oh, this is real. This is fake action. So generator and discriminator are fighting each other. And generator want to generate images so that discriminator doesn't know whether it's real or no. And discriminator want to train them so that it knows who is real and who is fake. And after all this min-max training, discriminator winning percent is 50% and the generator winning percent is 50%. Then it is optimal point of training. This is end of my class today. And probably from next Monday, I'm going to talk about variational autoencoder. And I think we should be patient. This is a lot of very difficult to understand, a lot of mathematics going on, but I think we should know. So, and tonight, let's have a good time. Thank you.